right, when we're wanting to analyze circuits of a whole bunch of different elements arranged in a way that, maybe we're doing the circuitry in a house, or we're looking at the circuitry in some type of electronic that has resistors and various elements, capacitors, and all arranged in all sorts of different ways to do all sorts of different things. We want to be able to analyze how much current is going to be drawn in a certain part of that circuit, for example, so that maybe not enough heat, that too much heat would be generated if a lot of current was going through a certain element of a circuit, and that could be dangerous. So our abilities to analyze circuits, currents, and the voltages and the resistance in a circuit relies on our ability to understand how circuits might be arranged. And there are two ways that allow us to simplify the circuitry, not necessarily down to a single element and a voltage source, but at least to simplify it in a way that allows us to manage really the analysis of that circuit in a much smoother and easier way. And so the first one we're going to talk about is circuit elements in series. The other way that we can arrange things is circuit elements in parallel. So these two videos, the circuit elements in series and the subsequent one that is circuit elements in parallel, or whatever, doesn't matter which order you watch them in, it's going to give us an idea of how do I take elements that are arranged in these certain ways and simplify them, turn them from one element of multiples or multiple elements together down to one single element of what's called an equivalent element. So we're going to look at all of the elements we've talked about, resistors, voltage sources, and capacitors, and how they look both in series in this video and in parallel in the other video. All right, so let's talk about what series means. Series simply means in a line, such that, I'm going to use resistors as my visual, such that the resistors are going to have the same current going through each one of them, with no break, no change, no decision for the current to make, no splitting along the wire. So it's as if one wire with these resistors added along it is all in one continuous line, okay? When resistors, so now we're going to talk about what happens when I put resistors specifically in series. So nothing is influencing the current as it goes through these three resistors. And it's as if I had one resistor that represented all three of these together, I would have kind of the same effect happening in the circuit. And that's the idea of an equivalent resistance. For resistors, when resistors are in series, the equivalent resistance, which we're going to call R equivalent, is equal to simply the sum of the resistors in that line. So simply the sum of the resistors in that line, as if multiple in the line are actually all one combined together. So for example, if we were going to have a circuit, remember we need all the parts to that circuit. So here I have my voltage source, and I have two resistors in a line where, let's say that this resistor is 2 ohms and this resistor is 4 ohms. My equivalent resistance, if I wanted to simplify this circuit, and instead of those two, I just made a circuit with one, what would be the resistance I would need so that these circuits produce the same outcome? And for my resistors in series, my equivalent resistance is simply R1 plus R2, so 2 plus 4, or 6 ohms. So this would be the same as if I had, this circuit would be the same as if I had a circuit with the same voltage source, but a single resistor of 6 ohms. So that's what we call an equivalent resistance. So it's going to be important, write this down for you to remember, that for resistors in series, they simply add together. Those are resistors. What about voltage sources? I'll use a different color. So for a voltage source, it is also possible to put voltage sources, batteries, We'll use batteries in series. In fact, you probably do. Like when you have that flashlight and you pop those 2D batteries into that flashlight, you're putting those batteries back to back to back. So if I were to draw that, it would be an example of 2 batteries in an appropriate series. So if they're connected, when batteries are connected low to high, so in the same orientation, the voltage equivalent is simply the sum of the 2 sources, and so on. So they get a larger and larger voltage source. A 1D battery is 1.5 volts. If I put 2D batteries into my flashlight, I now have 3 volts, 1.5 plus 1.5. So if I were to do the whole circuit, I'm going to pop, there's my flashlight. There's the light bulb in that flashlight. Okay, just to make sure we always remember there's kind of a resistor element that's going to be important. And this is 1 volt, 1.5 volts. And this is 1.5 volts. This would be the same as if instead of a 1.5 volt battery, I had a 3 volt battery. The outcome, the brightness of the bulb, would be the same in these 2 situations. Now, it's also possible that voltage sources are put in series in opposite directions, such that the voltages are put backwards. Now, if the 2 voltage sources are the same, then I'm going to actually have an equivalent voltage of 0. But if they're different, and this is used in when one is charging batteries, for example, my equivalent resistance is going to be the difference between these 2, and the direction of the current is going to be relative to the larger of the 2 voltages. So this would be as if I had a voltage source with the equivalent of 2 volts. All right. So we can also put voltages in series. When we do that, it's often our most consistent usual use is to increase the voltage of the device, or the circuit that we are trying to use. All right. The last thing are capacitors. So we can also put capacitors in series. Let's look at what that looks like and why. This is a little different. These have been sums. When we put capacitance, it looks a little different. All right. So we will use yellow. All right, so capacitors. When I put a capacitor in series, the equivalent, what I'm doing, let's draw it first. So with a capacitor in a circuit, it's 2 lines, not like a battery where one's shorter and one's longer, but both lines are of equal length. Why? Well, remember, we charge those plates up equally on both sides. All right, so there's our capacitors in series. Now let's put my voltage source on there. Notice the difference, long and short, 2 of the same length. When I think about the capacitance, the voltage across all 3 of these capacitors has to be the same as the voltage across here. Okay, so the voltage difference that is across the battery has to be the same as the voltage difference across these 3 capacitors. Why? Because these 2 lines never break, right? Never deviate from that path. And so the voltage drop across here, this is as if it's the same wire, okay? All right. The voltage then drop across this has to be then equal, if I talk about these as each having a potential, the potential across here has to be the potential. So if this is V, the sum of the potentials for each of those capacitors, okay? We know that the voltage on a capacitor is the charge per coulomb, right? The charge per capacitance. Sorry, the charge per capacitance. Okay, so if I know that the charge per capacitance, if I had a single, I want to convert this into, oops, I should use the same color. I want to convert this circuit into an equivalent circuit with a single capacitor of a equivalent capacitance, then this voltage V, the voltage from the battery, has to equal Q over the equivalent capacitance. We also know the voltage of the battery is the sum of these voltages, So that would be Q over capacitor 1 plus Q over capacitor 2 plus Q over capacitor 3. So this is V1, V2, and V3. So I pull Q out of that, I end up with Q times 1 over the equivalent capacitance equals Q times 1 over C1 plus 1 over C2 plus 1 over C3. So for capacitors in series, the equivalent capacitance, 1 over the equivalent capacitance, is 1 over C1 plus 1 over the capacitance of C2, and so on and so forth. So the inverse of the equivalent capacitance is the sum of the inverses of the individual capacitance. And that's kind of how we derive it. Right? So capacitors can also be in series. Okay. Either this was the second video we watched and you already looked at parallel, or let's go now to the parallel video and see how resistance, voltage, and capacitance looks in parallel. Good job.